Welcome, everyone. My name is John Carey, and a long time ago, I and a few colleagues started TechX, and we began releasing software for plasma simulation. I'll talk about that in just a minute, but this is the beginning of the TechX Worldwide Simulation Summit for 2022, and one of the big deals about this one is that we're introducing VSim 12. So I want to welcome you all, and I'm just going to say a few words here, and then I'll be handing it over to Dr. Andy Yu. So I think many of you who are here know what TechX is all about. What we focus on is plasma simulation, primarily with VSim. We do have an RSim product as well, but this is what we're mostly going to be talking about today. TechX Corporation provides simulation software that contains all of the needed physics for doing and modeling plasmas. It has charged particles interacting with external and generated electromagnetic fields, extensive collision processes, extensive boundary processes. It has complex geometry, and that truly sets it apart from other plasma simulation software packages. It's high performance. It can be run on anything from a laptop to a supercomputer. It's just the bigger problems you have, the more compute power you want. And it has ease of use with a nice graphical user interface. So to summarize, what we do at TechX is we bring the latest advances in physics and computational research to solve complex real-world problems, especially in the area of plasma physics. So TWSS, again, TechX Worldwide Simulation Summit, will describe and demonstrate the latest capabilities. You're going to see over the next few days, next 2 days, that we've greatly enhanced our reactions with an unlimited number of reactants products, and those can be limited to surfaces. You're going to see that visual setup has been significantly expanded so that you can now do external circuits, which is very important for doing things like magnetron sputtering or various kinds of arc breakdown. We now have the ability within the graphical user interface to do parameter scans, and we have a new word for analyzing those scans, and that's what we call scanalyzers. Please forgive us the portmanteau, but we're trying to move in the tradition. So another thing, you may recall me talking about speed limited particle and cell, I believe it was last year. And this is a way of keeping kinetic electron effects, even though you're studying slow ion scale phenomena, and doing so while eliminating the high frequency plasma effects from the problem so that one can solve them accurately, get the physics correct without the requirement of the very tiny time steps that typical electron simulations require. Well, last year it was under development, it was research, and now this year you're going to see that it is now available within VSim. And of course, we keep adding and putting more things in it. Now, this is especially good for the Townsend problem. The Townsend problem is originally a problem of breakdown between two plates where you put a voltage on it and you ask how much does the signal, the current get amplified by the fact that as the electrons are traveling through the gas, they cause ionization, which creates more electrons. So as we said, presented last year in VSim this year. Now, one of the cool things about that, I think, is that this allows people to compute breakdown. What happens in the Townsend problem is, of course, that when you get exponential growth, well, that tells you that the whole system is about to arc. And for many situations, what you'd like to do is figure out whether that breakdown is going to occur, because of course, if it does occur, then you'll have major problems with whatever device you're trying to design. So what one can do is combine those two things, the scans with their scanalyzers and the speed limited particle and cell and do a number of simulations of any particular configuration at a number of different voltages and look at each one of them and figure out, hey, did this simulation have exponential growth in the number of particles? Well, if so, breakdown occurred. Oh, it did not? Then breakdown didn't occur, and it's okay to operate at that voltage. So the ability to compute breakdown is really significant, we think. And then finally, there is the, not finally, but penultimately, there is video creation. This is a new feature in the GUI where you can stitch together your images and create a movie of it. And that's especially important. And I know that for many of you, what you're doing here is you are trying to do the physics that you need to do to help your company or your unit or do for your project. You want to try and do the physics that you need to do in order to get an answer about how to configure a product or whether or doing research in the university setting. Well, in order to do that with VSim, of course, you have to go convince your manager that VSim is a good product and it will help you do the physics you want to do. And there's nothing better than a good movie to help you make that convincing point. You're also going to see that we have tons of examples, new examples for breakdown, for magnetron sputtering, and more. And there will be a series of talks over these 2 days that tell you all about that. So I want to invite you then to just sit back and relax, enjoy the show. And I'd like to introduce our next speaker, Dr. Andy Yu, who comes to us from Boise State, where he got his PhD. And he has been a VSim user for a long time, even as a grad student. And now, of course, we're lucky to have him at TechX, or employed by TechX, because he's still located in Boise, but employed by TechX, where he's going to show you a number of the new features of VSim that are in VSim 12. So thank you.
Sure. All right, I assume everyone can see this fine. So welcome again. My name is Andy, as John said, and I'm an applications engineer at TechX. In my presentation today, I want to show you how you can use VSim to explore the fundamental physics of complex devices. I will use my own research in cavity magnetrons as the example here, but the general workflow applies to other research as well. I want to lead today's presentation with a quote from renowned French music conductor Nathalie Stoltzmann. There are 2 types of artists, those that strive their whole life to show how much what they are doing is difficult, and they do have their audiences. Then there are those who spend their life trying to make people believe that it is not at all difficult, which is the category I belong to. That is also probably a form of madness. It is less spectacular, perhaps, but I prefer that the audience be able to go to what is essential in the music. I do not want them to stop at being impressed with the performance, even though they might notice it, but that they may be able to abandon themselves in the beauty of the music. Although she was talking about musical performance, in this quote, replace every word music with the word science. I believe her principle applies to scientific works as well. With that, let's start with the essentials. The scientific method, everyone knows this. This is what brought humanity out of the Dark Ages, and this process is fundamental to all modern scientific progresses and understanding, and to a certain degree, I believe social progress as well. Although the method is often presented in this type of neat circular flow diagrams, as we all know, in practice, things can get a lot more stochastic, as we like to call it, a lot more random. For example, if your research is in a frontier area, there might not be much background information available for you to do your background research. In many situations, you might not even have a clearly defined hypothesis, or the results of your experiments might not be conclusive, etc. But in any case, testing and experiments are essential. This is not to say science is all about testing and experiments. Theoretical works provides the hypothesis to run experiments for, as well as providing tools for efficient data analysis. Now, contemporary computer-aided engineering, or CAE as people call it, these tools have matured to a point that the results they produce are widely regarded as data. Of course, everything ultimately needs to be verified by physical experiments, but physical experiments are not always feasible due to various constraints, especially in an early stage of a research. VSim as a CAE tool is essentially a testing and experimentation tool, which is useful for both experimentalists and theorists. Unlike traditional quote-unquote brick-and-mortar experiments, which in this day and age involves significant, sometimes prohibitive capital and human resource investments upfront, VSim allows contemporary scientists and engineers to perform the same experiments at a fraction of the cost, hence largely bypass the capital and human resource investment issue and makes contemporary science accessible to more people. And VSim has many advantages over other CAE tools, as you will see throughout this presentation. RF technologies have really become the backbone of many aspects of modern society. They have prominent uses in communication, as they are widely used for applications related to object detection, heating, and material processing. RF can be generated via the use of solid-state devices or via the use of microwave vacuum electron devices, or MVEDs for short. The use for MVEDs predates solid devices, but in the past few decades up to today, solid-state devices are very popular due to their versatility. However, with the ever-increasing needs for higher power and higher frequencies, people have begun to shift their focus back to MVEDs, such as Mangatrons, Klystrons, and traveling wave tubes, and others. The figure on the right shows time on the x-axis, and the y-axis is a figure of merit, which is a combination of power and frequency. It is average power to frequency squared in megawatts, gigahertz square second, a very big unit. As we can all see, in terms of combined power and frequency, solid-state devices have been mostly stagnating since the 70s. This is, of course, due to its physical constraints that electrons have to collide with the material lattice for the interaction to happen. And you have power and frequency limitations on that. In contrast, MVEDs have continued to push into higher and higher power and frequency combinations, almost displaying a Moore's law-like trend that is still continuing. Despite their extraordinary capabilities, MVEDs present significant challenges, since making them to work as desired is not always easy to do so, and the physics behind these devices are not always well understood. My research focuses on a type of MVEDs known as the Mangatron. I am interested in the fundamental physics behind its operation, especially its startup mechanisms and how to potentially control it. I want to mention here that the word Mangatron is used in many different contexts to mean very different things. You have cavity Mangatron, which is what I'm going to talk about today. And you also have sputtering Mangatrons, which we have a presentation for tomorrow morning as well. And you also have Mangatron injection guns that is used in devices such as gyrotrons, and these are different devices, although they're all called Mangatrons. So some background about the Mangatron. The Mangatron is one of the most common type of MVEDs that has many applications. Mangatrons have exceptional power efficiency, up to 90%, and very high power density. The Mangatron anode is a slow wave circuit which can take many shapes, as you can see in this figure on the top. A single Mangatron cavity can be viewed as a LC circuit, as shown in the figure below. The geometry of the cavities determines the inductance and the capacitance, which in turn determines the frequency of the LC circuit. The Mangatron can operate in many different modes depending on the phase difference between one resonant cavity and its adjacent cavities. Maximum efficiency is achieved when the phase difference between adjacent cavities is 180 degrees or pi. The resulting operating mode is known as a pi mode. Mangatron operation is a chaotic process. During the Mangatron's operation, the cathode emits electrons, and the electrons form a hub around the cathode. The Mangatron is a cross-field device, namely the applied DC electric field between the cathode and the anode is perpendicular to the applied magnetic field. This field configuration dictates electrons in the system following a E cross B drift motion described by the Lorentz equation. The electron motion induces current on the slow wave circuit, and the feedback fields from the slow wave circuit causes azimuthal velocity of the electron population to bunch, and electron spokes begin to form as a result of this bunching. This process can be seen in the figure on the right. In subplot D, we can see the Mangatron oscillating with 5 spokes. This is a pi mode for this Mangatron since it has 10 cavities. This figure comes from one of my simulation results, and we will come back to it later. The RF fields are supported by particles giving up their potential energies to the RF field. In order for this to happen, the applied E and B fields must fall into certain ranges and maintain certain relations. Lots of detailed physics here, but I will not go into the details since we have a general audience here. One thing that's important to mention is that Mangatron is a free-running oscillator by default, which means the RF phase of its output are not controlled. This significantly limits its use for applications that requires phase control. Finding ways to control Mangatron output phase is an active area of research, which is an area this research partially falls under. So what capabilities do I need to simulate such a device? First and most importantly, I need self-consistent simulations of beam wave interactions. A computational combination that can reliably do this is finite difference time domain and particle in cell. Second, since my device is a cylindrical device that involves curved surfaces, I need my simulation to use cut cells for accuracy. Third, it would be great to be able to do CAD imports to make it easier to work with complex geometries. And last, and also very important, I need to be able to finally control the spatial and temporal profiles of the applied field and particle emissions so that I can run experiments to explore the physics. As you can expect, VSim has all of these capabilities, so VSim works as a great tool for MVED research. 2 Mangatrons were modeled for this study. One is a 2D rising sun Mangatron, and the other is the CWM 75 kilowatts, which is a commercially available product from L3 Harris. Each Mangatron model was simulated under 3 different priming conditions, that is no priming, RF priming, and cathode modulation. The term priming here refers to creating a simulation environment that's favorable for Mangatron startup. Priming can be done via adding an external RF signal, modulating the electron injection, or varying the external magnetic field. Some of these techniques, such as cathode modulation, can be experimentally realized. Some of these techniques are mostly theoretical and help us to study device physics. I will not have time to go over all of these cases in detail. I will only go over a couple cases individually, then I will look at the results from all cases in aggregate, which is where the most interesting observations can be made. Keep in mind, the 2D model and the 3D model are of different devices. The rising sun Mangatron model have a 2D geometry with no scaling. The dimensions are shown in the figure and the table here. In this case, since it's a 2D model, RF output was simulated by a power absorber in one of the cavities, as you can see in the figure, type loaded cavity. The cathode emission boundary can be, in this case, is circular, as is modeled as a cylinder, but in actual Mangatrons, this cathode can take many shapes, sometimes a spiral, usually a spiral, and sometimes you'll have other exotic shapes as well. The simulation domain is 204 by 204 millimeter. The simulation cells are 2 by 2, so this is a relatively coarse simulation grid. But as you can see, it can still produce very good accuracy. The time step size delta t in this case is set to exactly 1/1000th of the pi mode RF period, and this is below the CFL limit. This time step is chosen very deliberately for our analysis later. And in this case, a 500 nanoseconds simulation takes about 1 to 2 hours with 32 CPU cores. And these are not even the latest CPU cores. So this simulation runs rather efficiently. Very quickly showing the 3D model specs as well. Note that this is a much larger simulation, and a 300 nanosecond simulation in this case takes about 2 days to complete with 32 CPU cores. And one thing I want to mention is in this simulation, a 10-sided cathode was used to simulate, for this simulation, to match a experimental configuration. And that is a cathode that was intended to be used with gated field emitter arrays to actually do this controlled injection that we are about to simulate. So it's not just a simulation concept, it's actually being experimentally realized. So first we simulate the device, the 2D device without any priming. This is our reference case. The model can start up very quickly without any priming in this case. This figure here in the middle shows the microparticle distribution at various time spots. In the beginning of the simulation, we can see the electrons being injected around the cathode. And a bit later in subplot B, at 100 nanoseconds, we can see the electron population is now showing a 3-spoke pattern, which corresponds to the 3/5 pi mode. Then at about 150 nanoseconds, the electron population begin to shift to the pi mode, which give you this 5-spoke pattern. And at 250 nanoseconds in subplot D, this Mangatron is fully oscillating. And the figure on the right shows histories of cavity voltage, the emitted current along with absorbed current by the cathode and the anode, the physical particle count, and the output power. The current plot shows a noisy pattern before 200 nanoseconds and 350 nanoseconds, which suggests instability, possibly caused by mode competition. Then after 350 nanoseconds, the device seems to be operating in steady state. With the stabilization of cavity voltage, current, particle count, and output power. So the particle position plots and history plots are the most common ways to look at simulation results. While offering us with many useful information, they do have their limitations. The particle position plots show us where the particles are located at a certain instant of time, and we can observe this plot and see whether the patterns matches or our expectations and identify potential issues. However, one plot only shows one instance of time, and many plots are needed to see progression, as you'll see on the previous slide. 2D cross-sectional plots may omit important information if the simulation is in 3D. And 3D particle plots can be hard to read. And more critically, these plots offers minimal information about the particle's movements. The history plots show us macro level quantities of interest. These are usually numbers representing certain aspects of the total system. While revealing many useful information, these macro level quantities often fail to capture micro level activities, which are often critical for understanding settled device physics. So it is natural to wonder, what if we can have an analysis method that shows the behaviors of the particle population and how they change over time, so that we don't have to try to analyze large collections of particle positions or velocity plots? And what if we can have an analysis method that generates statistics of the particle population's movement and how they change over time? So my first solution is the electron distribution intensity plots, as shown here. Each plot shows the normalized probability masses of an attributes of interest and how they change over time. The generation of these plots involves a lengthy process. I will not go over the details for the sake of time, but I want to point out that this type of processing is possible because VSim allows the user to access the complete suite of data of every particle in the simulation. That includes positions and velocities in all directions, the microparticle weights, and even the particle tags that allows distinct particles to be tracked across data dumps on a massive scale. So the first attribute of interest is the radial position, as shown in subplot A. This plot shows the position distribution of electron population in the radial direction. Darker color denotes higher probability in this case. For example, in the beginning of the simulation in region 1, we can see that areas near the cathode are very dark, and areas near the anode are white. This means that it is very likely to find an electron near the cathode and nearly impossible to find an electron near the anode in the beginning of this simulation, which is what we expect. Also in region 1, we see the dark areas expanding towards the anode, which indicates electron population is expanding in the radial direction. And the electron population reached the anode in region 2. The same analysis was done to radial velocity as seen in subplot B. We can see that in the beginning of the simulation, the radial velocity distribution has a balanced spread near 0. When charge transfer began to happen in region 2, which is when the Mangatron began to oscillate, the distribution shifts into the positive regime, which is consistent with our expectation for charge transfer. The azimuthal position plot is unique since the azimuth of the cylindrical geometry forms a complete circle, so the bottom of this plot is actually connected to the top of the plot. Since the time step delta t is exactly 1/1000th of the RF period, and electron data was dumped every 1000 steps, electron data was dumped as the exact end of every RF period in this case. Therefore, if the device is indeed oscillating in the pi mode, the azimuthal position plot should have 5 perfectly horizontal lines. Deviation from these lines indicates frequency instability. In this plot, we can clearly see that the pi mode pattern emerging out of chaos. The fuzzy lines in region 3 indicates frequency instability, which confirm with our previous observation that we have mode competition in the system during that regime. And azimuthal and the lines in region 4 is quite clean, indicating the frequency is stable. The azimuthal position plots given the appropriate data dump period functions as a great diagnostic for frequency and phase stability. The azimuthal velocity plot also shown, that is subplot D, also shown the previously observed instability in region 3 with its spiky patterns. Works are currently being done to compare this azimuthal velocity distribution to the phase of the RF circuit. In this plot, red lines denotes average. The oscillating pattern in region 3 again indicates instability, and the flat averages in region 4 indicates stability. If you are familiar with analysis of particle data, the electron distribution intensity plots are essentially phase space plots with the added dimensions of time. These plots free the researcher from sliding a time bar up and down and sense information and shows information throughout the simulation. And since all the information is displayed on the same plot, it makes key pattern a lot easier to recognize, as you can see, especially in subplot C. The other new analysis technique is the breadth ratio analysis. For this analysis, we first define a nominal direction of movement for each axis. In the context of our cylindrical magnetron, the nominal direction of movement in radius is a positive radial direction, since we want electrons to flow from the cathode to the anode. The nominal direction of movement in azimuth is a positive azimuthal direction, since the direction of our external magnetic field dictates the electron spoke will rotate in the positive azimuthal direction when the device is oscillating. Now, at a given time spot, if particles have a positive velocity in the nominal direction of movement, we call this particle an advancer. If the velocity direction is counter to the nominal direction of movement, we call this particle a decliner. And the breadth ratio for each axis is simply the ratios between advancers and decliners. In short, the breadth ratio in radius reveals the level of internal support for charge transfer from the cathode to the anode. We will explain this when we look at a specific plot. And the breadth ratio in azimuth reveals the cycloidalness of the electron population. It's not only reveals, it actually quantifies it, because the ratio is a number. It's a simple number. As shown in this illustration here on the bottom, on the top right, subplot A shows a highly cycloidal electron trajectory. In this case, a significant portion of the electron trajectory is in the declining state as indicated by the blue arrows. And in this case, the breadth ratio in azimuths would be very low because it's essentially the comparison between the length of the green vectors versus the length of the blue vectors. If the electron trajectory was less cycloidal, as in subplot B, a lesser portion of the trajectory would be in the declining state, which will lead to a higher breadth ratio in azimuths. If the electron trajectory is near Brion flow, that is, it is not cycloidal at all, as shown in subplot C, then the breadth ratio in azimuths would ideally be infinite in this case, since we have no declining states. Now let's look at the breadth ratios for our simulated electron population in the rising sun Mangatron in the bottom plot. In region 1, we can see the radial breadth ratio stays around the 1-to-1 level. This means for every electron moving towards the anode, there's an electron moving away from the anode. As a result, the electron population has no net movement towards the cathode. The ratio begins to take off in region 2 and wildly oscillating in region 3, again indicating instability in region 3. And then in region 4, the ratio holds at about 3.8 to 1, which means for every 3.8 electrons moving towards the anode, there's only 1 electron moving away from the anode, indicating a net movement towards the anode with the radial breadth ratio holding at 3.8 to 1, the electron population offers continuous support for charge transfer from the cathode to the anode. And for the azimuthal breadth ratio in subplot B, we can see the ratio stayed quite low prior to oscillation start. And more interestingly, even after steady state was reached, this indicates that the electron population was highly cycloidal before and even after the device oscillation reaches steady state. We will discuss the 2D and 3D results together in later slides. The point of this slide is to show you the type of control that VSim gives you. In this case, I want to inject electrons at 5 evenly spaced locations that rotate around the cathode to match the phase of the RF field. This uncommon simulation setup was to accompany the experimental setup that we were doing. In VSim, you have complete control over where and when particles are emitted and introduced into your simulation. In this case, my electron injection was described by this very messy function you see under the third bullet point. And the result of this function, as you can see in the particle distribution plots in the middle top plot, is that we have exactly what we want in this case. We have injected electrons at 5 distinct locations, and these locations rotate to form this oscillation. Lots of work was done analyzing the simulation results. Here I will only show you the most exciting parts. Some interesting patterns become obvious when we put the breadth ratio plots of all cases together. That's all 6 cases across the 2 different models. The plot in the middle shows the rising sun Mangatron cases, and the plot on the right shows the 3D CWM 75 kilowatts simulation cases. And out of all 6 cases, we have 4 cases that reached stable oscillation. The cathode modulation case for the 2D has some issues, probably because the way I was doing the cathode modulation kind of fights with the rising sun geometry, because it's a it's a sort of a specialty geometry that have multiple modes in there. So that case didn't work all that well. So we can omit that case. And the other case that didn't reach oscillation was a no priming case for the 3D model. So chances are I still need to optimize this model, because there is a research paper by University of New Mexico that was managed to make this model oscillate without priming. So we omit those two cases and we look at the 4 cases that oscillate. So we can see a stable startup always results in a breakaway and hold pattern in the radial breadth ratio plots, as you can see in the no priming and RF priming cases for the 2D and the RF priming in the 2D. So right, and more importantly, in all cases that oscillated, the azimuthal breadth ratio always dipped lower right before oscillation starts, as you can see in the 4 cases that oscillates. So one note on the breadth ratio, on the radial breadth ratio for the 3D case, you can see it's try to break away, then it fails. This is caused by the way that when those spokes touch the anode circuit in the beginning, it formed something we call a super spoke, that the anode begin to suck particle out of the system very rapidly. So that causes the azimuthal, the radial breadth ratio to collapse, as you can see here. And I have discussed with some industry people, and I have been informed that in Mangatrons like this, sometimes you go through several of those startup and breakdown cycles before a steady state is reached. And in this case, my simulation ended at 300 nanoseconds, so I don't have a chance to see that. But the observation in azimuthal breadth ratio is what we want to focus on here. So more interesting observations can be made when we look at the analysis plots from a different perspective. These plots shown here are from the 3D simulation of the CWM 75 kilowatts. But the same observations were also made when studying the 2D results. Here are the observations. We know that oscillation startup requires a radial expansion of the electron population to open up the possibility of charge transfer from the cathode to the anode. This radial expansion can be clearly seen in the radial position distributions on the very top. However, if we look at the radial breadth ratio, that's the 2 subplots on the bottom, during when the radial position was expanding, we see that the ratios remain flat, which indicates that the radial expansion of the electron population is not supported by the electron population's net radial motion, which is counterintuitive. At the same time, we see the timing of the azimuthal breadth dip coincides with the timing of the radial expansion of the electron population, suggesting strong associations between the two. The reason why I use the word association here is that note near the end of this simulation, the azimuthal breadth ratio is also very low, but the electron population did not expand or show the same expansion pattern, which means the azimuthal breadth ratio dip is likely a necessary condition for radial expansion of the electron population, but it is not a sufficient condition. There are other factors also at play here. So what does this tell us? The hypothesis I have is that the increased cycloidal motion of the electron population creates a very dense electron population near the cathode as the electrons turn around in their cycloidal orbits. Because the velocity is very low when they make their cycloidal loop, the electrons spend more time near the cathode, as seen in the radial position plots. As a result, electrons are propelled from the cathode due to the Coulomb force and cause the electron population to expand towards the anode. So that's the new hypothesis. So let's summarize what the process so far. So we started with a hypothesis that is not well defined because theories on Mangatron startups are incomplete. We proceed by simulating two different Mangatrons under various setups. Some of these setups are inspired by physical experiments and obtained trustworthy results from VSim. We analyze the results with standard techniques as well as finding new techniques to look at old results in new ways. And we made observations that lead to updates and modifications to our original hypothesis or the forming of new hypotheses. Then the natural next step here is to repeat this cycle and test our new hypothesis. So in previous results, we see that the breadth ratio consistently dip, the azimuthal breadth ratio to be specific, consistently dip prior to oscillation start, and concluded that there may be association between the azimuthal breadth dip and Magnetron startup. So it would be natural to see what would happen if we inject electrons in ways that induces low azimuthal breadth ratios. The way I did this was by what I call electron counter injection, which I define as the act of emitting electrons from the Mangatron cathode with an initial azimuthal velocity with a direction that is counter to the direction of expected rotation determined by the direction of the applied magnetic field. So electron counter injection is expected to increase the level of cycloidalness of the electron population because with previous terminology, you are essentially adding decliners into the system. For the sake of simplicity in this study, I fixed the initial azimuthal velocity with an amplitude of about 5.3 10⁷ meters per second in the counterclockwise direction. This velocity was determined by iterative parameter sweeps, and this velocity seems to induce the pi mode oscillation the best. Now the level of cycloidalness can be altered by changing the percentage of electrons that are counter-injected. The ratio of counter-injection was swept from 0 to 1 in 0.1 increments. So this type of analysis is where the parameter sweep come in very handy when you need to run a massive amount of the simulations. So in this case, for each, I run 11 cases for total. The difference between the three group of plots you see here are time, which is labeled on the bottom of each group. So in this case, a ratio of 0, when the ratio is 0, all electrons were injected uniformly, which is our reference case. On the other hand, when the ratio is 1, all electrons were counter-injected. By the same logic, a ratio of 0.6 indicates 60% of the electrons were counter-injected, while the other 40% are injected uniformly. The left plot is at 25 nanoseconds, which is very early on in the simulation, and the middle group is at 75 nanoseconds, and the right group is at 150, which is right before the onset, which is as the onset of oscillation. Lots of information here, and I don't have time to go through everything, but I want to mention 3 most important implications of this study. So the first implication is that electron counter injections have effects on the startup process, as you can clearly see. Though the physical mechanism by which these effects takes place are not yet clear at this point. And second, electron counter injection, when applied correctly, clearly speed up spoke formation and shortens oscillation startup time, as you can clearly see, especially in this middle plot. When the counter injection ratio is 0, you are still struggling with the 3/5 pi mode, and with a higher ratio, you can begin to see the 5-spoke pattern already. So the third implication is that after the Mangatron is oscillating, which you can sort of see in the right plot group, counter injection seems to be of no further help to the characteristic of the oscillation. Rather, it's actually as noise in this case. So ongoing work includes continuing this electron counter injection study, developing new analysis techniques, and extending this type of research to other MVEDs. I will not go into the details for this since most ideas and results have not been published. But I do want to mention is that work is being done to integrate the electron distribution intensity plots and breadth ratio plots into the VSim ecosystem, so that all VSim users will have easy access to these analysis techniques presented earlier in this presentation. This presentation have demonstrated that VSim with its robust algorithms produces trustworthy results. VSim grants its users complete control over the simulation and will not stand in your way when trying out novel setups. Besides its built-in data visualization and analysis capabilities, VSim also allows easier integration with most programming languages for sophisticated data processing. With all these pieces in place, VSim serves as an essential link in the scientific process. But this work was conducted under the direction of Dr. Jim Browning, who was my PhD advisor, and I would also like to thank AFOSR for funding this research throughout my grad school. And here is a list of publications and presentations that was based on this research. And with that, I will take any questions you may have, but please keep your questions general for general audiences here. If you are interested in a discussion regarding specific technical details, please email me directly at the email listed here. And yes, I do read all my emails. So if you want a discussion, just email me. And let's see if there are questions.
Yeah, that was fantastic, Andy. Thank you so much for doing that. As Dr. Carey said at the very beginning, we are certainly pleased that we have Andy here as an application engineer for us. There is a Q&A box where you can type in questions on the bottom and I can read them. Andy also put his email there, as you see, which in many cases is a little bit easier than with asking the questions here, especially if they have a lot of technical details, and we definitely want to assist you. Our next talk is coming up in just a few minutes, and that's going to be Dr. Ming-Che Lin. So I think maybe one or two, if you want to type them in the Q&A box, and we can take them. Otherwise, we'll move on to the next. We have, for the rest of the day today, we have 2 more presentations, and then tomorrow we will have 3. We also have, Andy is so kind that he's going to deliver this for us again tonight to reach our clients over in China and Japan and all that, since it's a little challenging for them.
I see we have a raised hand by Robert.
Yeah. Let's see. I'll try to. Can you type your question in the chat box, Dr. Bob Terry? If possible. That was really good, Andy. I'm so excited to actually be able to see a little bit more of your background, you know, and the stuff that you've done before coming here. I still remember when Andy applied to work with us and I was like, oh my gosh, he's been using VSim this whole time. We were super excited that we were able to convince him to come be with us. So if anyone has one last call.
I don't see the question yet. So maybe just email me directly and we'll have 4 minutes till the next presentation.
Yeah,
So
that's
let's
fine.
keep on
We'll go ahead
schedule.
and yep, we'll go ahead and get Ming Che set up. So thank you again, Andy. Thank you very much.
Thank you.
And I will go ahead and we'll get Ming Che and his presentation coming up in just a few minutes. Thanks so much.